This is the third episode of the video lesson series on the laws of thermodynamics. Here we are going to study about the property entropy. Actually, this is a continuation of our study on the second law of thermodynamics that we started from the episode 2, because the concept of entropy was emerged from the second law of thermodynamics. Since this is a continuation of the second episode on laws of thermodynamics, this lesson also supports the achievement of the intended learning outcomes established in episode 2 that you see on the screen. The Clausius inequality, that is also known as the Clausius theorem, is an important corollary of the second law of thermodynamics. This inequality is said to be first stated by a German physicist called Rudolf Clausius. Now you can see for thermodynamics laws, there are many scientists are involved because the field of thermodynamics was developed through empirical observation. So many people involved in the development of the field of thermodynamics. The inequality says for a thermodynamic cycle, the cyclic integration of heat transfer divided by the temperature where that heat transfer took place must be either equal to 0 or less than 0. It is very important that you must perform this integration covering the entire cycle, not just part of it. That is what indicated by this cyclic integration notation. You perform the integration throughout the entire cycle. From every point where there is a heat transfer, you consider that one into this integration. Then only this relationship is valid. So that is a very important thing that you must remember. Let me explain you that with this heat engine cycle. Now here, interaction of heat is taking place at two places. Place number 1 is at the boiler, place number 2 is at the condenser. If the turbine and the compressor or the pump, if these are well insulated or perfectly insulated together with this piping, then you can consider there's no heat transfer across either tubes or across the turbine or the compressor. Therefore, only place where heat transfer takes place is boiler and the condenser. Cyclic integration of delta Q over T. Here we consider the boiler first. Delta QH divided by temperature of the boiler, because that is the temperature where the heat transfer is taking place. And here QL is a negative quantity, that's why you got a minus sign here, because QL is rejected, it's a negative sign. So delta QL divided by the temperature where the heat transfer take place, which is TL, that must be less than or equal to 0. Since the heat transfer at the boiler as well as condenser are taking place at constant temperature, you can take temperature out of the integration because it's a constant. It is a constant because those are thermal reservoirs. Therefore, it is simply integration or summation of heat transfer. Therefore, you get your equation QH divided by TH minus QL divided by TL, that is less than or equal to 0. That is from this Clausius inequality. You may recall the thermodynamic temperature scale that we learned in episode 2, which was developed using reversible heat engines. In that it says the ratio of heat transfer is equal to the ratio of temperature when the temperatures are expressed in Kelvin. Now here QH over TH minus QL over TL less than or equal 0. But for a reversible heat engine cycle, from the thermodynamic temperature scale, you know that QH over TH is equal QL over TL. That means This equality applies for reversible thermodynamic cycles, or at least if they are internal reversible. If the cycle is irreversible, then the inequality applies. We can interpret our understanding this way. If the quantity cyclic integration of delta Q over T, if it is less than 0, it is an irreversible cycle. If it is equal to 0, that is a reversible cycle. If it is greater than 0, it is impossible. You can't have a cycle like this. So this gives a kind of an indication to investigate whether a process is, or whether a thermodynamic cycle is possible, or whether it is impossible. This is in fact a very important theorem which subsequently led to the development of the concept of entropy as well. We can prove the Clausius inequality or Clausius theorem this way. Let's take a reversible heat engine which takes heat from a hot reservoir which is at temperature TH, and it absorbs delta QH quantity of heat and produces delta reversible quantity of work while rejecting delta Q amount of heat to another system. This is a piston cylinder device. And that piston cylinder device, or that particular system, is producing a work delta W system, because you are supplying heat, so it is expanding, therefore it can do some work. This heat transfer takes place at a temperature T, which is a variable temperature. Obviously, this is not a thermal reservoir, so T is varying, but the interface temperature at the moment is T. For the reversible engine that we are talking here, we can say delta QH over TH is equal delta Q over T. That is from the thermodynamic temperature scale. Now let us combine these two together. Reversible heat engine plus this our piston cylinder device. The total work performed by this combined system is delta W combined. That is equal delta W reversible from the heat engine plus delta W system. From the first law to the combined system, we can write that is Q minus W is equal delta E. The heat transfer is delta QH. Work transfer is delta W combined is equal DEC, the change of total energy of the combined system. We are considering about cyclic systems or cyclic devices. Therefore, when the combined system undergoes a thermodynamic cycle, there can't be change of total energy, because initial state and the final state must be identical, and energy, total energy, is a property. Therefore, it is equal to 0. Then we will get our equation delta QH minus delta W combined equals to 0. By combining equation 1 and equation 2, we can rewrite delta W combined is equal TH times delta Q over T. If you integrate both sides, then you will get the total work transfer, that is equal TH, which is a constant, so you can take it out of the integration, and integral delta Q over T. Now carefully look at this combined system. Now it is producing a work. It is producing a work while there is only one heat interaction. In other words, while it is interacting with only one thermal reservoir, it is producing a work output. This is a violation of the second law of thermodynamics, because it violates the Kelvin-Planck statement. Therefore, we can clearly say W combined cannot be a positive quantity because it cannot produce a work output while interacting only with a single reservoir. Therefore, this equation must be less than or equal to 0. That means cyclic integration of delta Q over T must be less than or equal to 0. This is a point where the concept of entropy was emerged. Remember, the concept of temperature was emerged from the 0th law of thermodynamics, and then the concept of energy or the internal energy emerged from the first law of thermodynamics. Similarly, the concept of entropy was emerged from the second law of thermodynamics. It says there exists a property of a closed system such that a change in its value is equal to integration of dq over t for any reversible process undergone by the system between state 1 and 2. It says this is a property of a closed system, but it does not mean it is applicable only to closed systems, because if it is a property, it doesn't matter, right? But this definition or that particular observation or that hypothesis was developed considering closed system. You remember the internal energy concept was also developed for closed systems because it is easy to observe. And it says the closed system undergoing reversible processes, right? It's very important. This definition is valid for reversible processes only. So proof of this corollary can be made by method of contradiction if we take the Clausius inequality as valid. Let's try to prove the corollary. Consider two reversible processes, namely A and B. A and B, which brings state 1 to state 2. Both A and B processes bring the state from state 1 to state 2. The process C is a reversible process which brings state 2 back to state 1, making a complete thermodynamic cycle. In fact, this creates two thermodynamic cycles, cycle AC and cycle BC. If we recall the corollary, it says there exists a property of a closed system whose value change is equal to the summation or the integration of heat transfer divided by the temperature where heat transfer takes place for any reversible process. That means if you perform that integration along path A or along path B, end result must be identical because it is a thermodynamic property. Thermodynamic property does not depend on the path it follows. That's why those are called as point function. Since we are going to prove by method of contradiction, let us take the opposite of the corollary as true. That means we are going to take that integration of heat transfer divided by the temperature along path A is different from the same along path B. Let us calculate the cyclic integration of Q over T along path AC and BC. The cyclic integration along path AC is integration along path A plus integration along path C. Similarly, the cyclic integration of Q over T along path B is integration along path B plus integration along path C. But from the Clausius inequality, we know cyclic integration of Q over T must be either less than or equal to 0. But the processes that we are considering here are reversible processes or reversible cycles. Therefore, cyclic integration of Q over T along path AC must be equal to 0 and the same along path BC must be equal to 0, because cycle AC and cycle BC both are reversible processes. Therefore, the equality of the Clausius inequality applies in this context. Therefore, 1 and 2 equations are identical, so we can write it like this: integration of Q over T along path A from 1 to 2 plus 2 to 1 Q over T along path C equals integration of Q over T along path B plus integration of Q over T along path C from 1 to 2. By looking at this equation, you can see these two quantities are identical. Therefore, it will cancel out. The end result is integration of Q over T along path A from 1 to 2 is equal to the integration of Q over T from 1 to 2 along path B. What this result yields is the integration of Q over T is independent of the path. Therefore, it must be a property. That means our assumption is wrong. Our assumption is the opposite of our corollary. Therefore, we can say the corollary is true. The property whose change of value for a reversible process found from integration of Q over T is called as the entropy. Entropy is an extensive property. That means it depends on the scale, or depends on the size, or depends on the mass. Therefore, total entropy is denoted by capital S and specific entropy is denoted by simple S. The results can be expressed this way: delta S or S2 minus S1 is integration of Q over T. In fact, it is here Q is delta Q. Or we can express that ds is equal delta Q over T. It's very important that you must remember this. These equations can be applied only if the process is reversible, or at least internally reversible. If the process is irreversible, then you cannot apply this equation to find out what is the change of entropy. That is a very important thing that you must remember. These two equations, which are identical actually, are applicable only if the process is reversible. If the process is irreversible, the entropy change cannot be found from this equation. The absolute value of entropy cannot be found from this equation even for a reversible process. For that, we have to consult the third law of thermodynamics. You may recall that we learned in the previous episode that if a process is reversible and adiabatic, it is called an isentropic process. That means there is no change of entropy. You can see it from here. If the process is reversible, then this equation is valid. And if the process is also adiabatic in addition to reversible, delta Q is equal 0. Therefore, obviously, delta S is equal to 0. That means change of entropy equals to 0, telling us that there's no change of entropy. Also, you can note from here, if heat is supplied to the system, entropy increases. Imagine in a reversible process, if heat is supplied to the system, entropy increases, and if the heat is rejected from the system, entropy decreases, because delta Q become a negative quantity, or heat transfer is a negative quantity because it is rejecting heat from the system. If you want to decrease the entropy, you have to reject heat. But increasing the entropy is not only associated with heat transfer to the system. If there are irreversibilities, entropy tend to increase. That's why you cannot apply this equation for irreversible processes to find out the change of the entropy, because irreversibilities also increase the entropy in addition to heat transfer to the system. I'll give you a simple question to try. Derive the SI units of entropy and specific entropy. I'll give you 10 seconds. Entropy, kilojoules per Kelvin, or specific entropy, kilojoules per kilogram per Kelvin. That is the answer. Principle of increased entropy is another very important concept or a corollary of the second law of thermodynamics. In some texts, people used to express the second law using this corollary as well, because that's very important corollary in the second law of thermodynamics. It says the entropy of a closed system which is thermally isolated from the surroundings either increases, or if the processes undergone by the system is reversible, remains constant. This is very important. Here we are talking about closed systems which are thermally isolated from the surrounding. Closed systems that are thermally isolated from the surroundings are isolated system, because there's no heat, no mass transfer. For such systems, the total entropy in the best case will remain unchanged, otherwise it will increase. It will remain unchanged only if the processes happening inside the system are reversible processes. But you know, in practice, reversibility is not something that we can practically achieve. Therefore, it will continue to increase the entropy. This is completely different from the concept of energy, because energy is a conserved property where the total quantity is constant, but entropy by nature it is not a conserved property. It has a tendency to increase the entropy. Actually, all processes that takes place in a direction where it can increase the entropy. That's why certain chemical reactions are taking place only in one direction spontaneously. That's why an inflated tire will release air to the atmosphere when there's a puncture happen. You can explain the behavior of many things based on this. And in fact, this is why heat will not flow from a cooler body to a hotter body, which is also explained by the Clausius statement as well. But you can see from this increase of entropy principle as well. Heat will not flow from a cooler body to a hotter body by its own. We can prove the increase of entropy principle. Let us take the case 1 for reversible processes. For a reversible process, we know change of entropy can be expressed by dq over T. If the system is an isolated system, there is no heat transfer associated with that one. So it is an adiabatic system, then dq equals 0. When dq equals 0, ds is equal 0, there is no change of entropy. That is the best case scenario, where there is no entropy generation. But in order to achieve that one, the process must be a reversible process. Let's take the second case, an irreversible process. Consider an irreversible adiabatic process A that brings a system from state 1 to state 2, and also a reversible process B that brings the system from state 2 to state 1, back to the initial condition. Remember the categories of the two processes. Process A is irreversible, but it is adiabatic. Process B, which is reversible, but it is not adiabatic. Although process A is irreversible, since it is adiabatic, integration of dq over t along path A must be equal to 0, because this is summation of heat transfer divided by the temperature where the heat transfer takes place. Since it is an adiabatic process, dq over t is 0, because dq equals to 0. You can perform this integration, there's absolutely no problem. Only thing is, this is not equal to the change of the entropy because it is an irreversible process. However, for process B, the same integration from this time 2 to 1, dq over t along path B represents the change of the entropy, because process B is a reversible process. Then if you take cycle AB consists of process A, which is an irreversible process, and process B, which is a reversible process. Since one part of the cycle is an irreversible process, cycle becomes irreversible. Therefore, from the Clausius inequality, we can express cyclic integration dq over 2 for cycle AB must be less than 0, because it is an irreversible cycle. You can expand the cyclic integration this way. So cyclic integration dq over t along path A and B is equal integration of dq over t along path A plus the integration of dq over t along path B. That must be less than 0. However, since process A is an adiabatic process, we know that dq over t along path A equals to 0. Therefore, we get S1 minus S2 is less than 0. S1 minus S2 came from here, right? Because 1 to 2 dq over t along path B is equal change of the entropy. That will give us S2 is greater than S1. Entropy at stage 2 is greater than the entropy at stage 1. So entropy is generated. The principle of increased entropy says delta S of an isolated system must be either greater than or equal to 0. Equality holds for reversible processes happening inside the system. A system can comprise of several subsystems. Let us study this a little bit further. Now take for example a particular system, for example a hot cup of a tea. Then your system, your thermodynamic system is the cup of tea. And the atmospheric air surrounding the cup of tea is your surrounding. But it is possible for you to draw a fairly large boundary where the system is not making any influence to that particular boundary. So that boundary is an adiabatic boundary where there is no heat transfer is taking place. Then you can consider this whole thing as your isolated system. The whole thing as your isolated system, which comprises of the system, that is your hot cup of tea and its surrounding. This is fairly big. Then we can apply the principle of increased entropy to this one. According to the principle of increased entropy, the total change of entropy of the isolated system comprises of the change of entropy of the system plus change of entropy of the surrounding. From the principle of increased entropy, it says delta S total must be greater than or equal to 0. That means change of entropy of the system plus change of entropy of the surrounding must be greater than or equal to 0. Equality holds for reversible processes. So it's very important to understand here we are talking about the total entropy of our isolated system. Entropy of the system can decrease and entropy of the surrounding can also decrease, but when you add them together it must be an increase. If you take for example the hot cup of tea example, when heat is rejected from the cup of the tea to the surrounding, definitely entropy of the hot cup of a tea decreases. So delta S system becomes a negative quantity. Since that heat is gained by the surrounding, entropy of the surrounding increases. So individually either system or the surrounding can decrease its entropy. There's no problem with that. However, when you take system and surrounding together, its entropy must be greater than or equal to 0. In all practical scenarios, it must be greater than 0 because there are irreversibilities. We can summarize our understanding this way. So delta S total in this case, delta S of that isolated system, if it is greater than 0, it is an irreversible process. If it is equal to 0, that means it is a reversible process. But if it is less than 0, that means it is an impossible system. That is an impossible system. You can analyze all the practical things using this concept. Like a hot cup of a tea is getting even hotter by absorbing heat from cooler surrounding. If you calculate the total entropy, you will get it will be less than 0. If it is less than 0, that means process is impossible. So this is a very handy tool for us to determine whether a hypothetical process is really possible or not. Chemical reactions and many other real world things happen in a direction where the total entropy tends to increase. The higher the irreversibility is, the higher the entropy generation. In practical world, we cannot get rid of irreversibilities. Irreversibility is there, therefore entropy increases. So we should strive to minimize the entropy generation. That's all what we can do. We can't eliminate entropy generation because we cannot eliminate irreversibilities. So every effort must be taken to minimize the entropy generation. Because if the entropy generates, quality of the energy decreases. Temperature entropy diagram is a very important diagram that you will deal with in this course module. When we study gas power cycles, when we study steam power cycles, we will extensively use this temperature entropy diagram. I'll give you another question to try. Plot the Carnot heat engine cycle on a TS diagram. Please pause this video and give it a try. Although we talk about entropy, how it emerged from the second law and entropy related corollaries of the second law, we did not discuss what exactly entropy is and its characteristics. Actually, the question what is entropy is a very heavy question because still there's no complete understanding of the entropy, and also entropy is not something that we can feel. And if you look at internet, there are a lot of misinterpretation of the term entropy because sometimes people confuse this one with the entropy in information science as well. So if I want to make a very clear video lesson on that, it will take fairly long time to make. Since we are having lectures in the class, I will skip this section to cover in the lecture. Therefore, while we are having the discussion, you can ask any questions, anything unclear. That will be, I guess, the easiest way for us to understand the concept entropy. With that, I will conclude this video lesson. And here we learnt about the Clausius theorem, principle of increased entropy and also TS diagram, change of entropy, and slightly about entropy, how it emerged from the second law, etc. So as usual, play this video as many times as you want until you fully comprehend the content, and then try the formative assessment questions on the Moodle together with this Muddiest Point exercise. Here you have to list 3 most confusing concepts learned in this lesson. It's not like listing certain things. You have to specify what is your confusion there. Then only it will reflect deep learning. As usual, you must answer the question 4 hours, at least 4 hours before the next lecture. Thank you.